So we will start a new topic after data converters. Some few points about mixed signal layout, because it is good to know for students who want to work in mixed signal, specifically for high frequency designs. And if we get time, we will have some introduction to PLL, which will be the next topic. Okay, so you may have heard about floor planning. When you want to make a layout or physical design, you want to know that where you want to keep your modules. This is called floor planning. Just you have a set of modules, black boxes. You want to arrange them like a puzzle in such a way performance of the circuit will be minimally optimized. So this is called floor planning. So what affects the floor planning when we are talking about a mixed signal circuit? So we have to be worried about analog signals which are sensitive. What do we mean from sensitive analog signals? Suppose you have an analog signal which has a very small amplitude, right? Therefore, it's a sensitive signal. And any node associated with that signal is a sensitive node. Or, for example, you have a high impedance node. That is a sensitive node because it can easily couple to any noise source in the circuit. So these are sensitive nodes or signals that we have to take care of them. Okay? And then when we do floor planning, we have to be careful how we want to route afterwards power supply and ground. It's not like that floor planning and routing are independent of each other. Because it depends how do you put VDD and ground or VSS lines. Because VDD and VSS are not clean. Always they have a lot of noise. The reason is because we are talking about a mixed signal system. In a mixed signal system, you have a digital module with a lot of switching. Therefore, your VDD and ground are not very clean. Of course, this question may come to your mind like, okay, but the effective resistance of these lines are too small. Therefore, effectively, any switching will not create any noise or we can call it bouncing on the signal. But then we will see what are the reasons for these types of bouncing. Therefore, we have to be careful about power supply and grounding when we make a floor plan. And also when we want afterwards, of course, route. And then finally, we have to take care of all modules in the same way that we do on breadboard. Means that we have to have shielding, we have to have proper guardings. So then what is guarding, what is shielding, what is the difference between these two? So just as an example, I want to design a floor plan a mixed signal circuit. I have an analog section, I have a digital section, and then digital section has high speed, low speed modules. It has drivers which go onto the pads and then drive output signals. I have driver in analog signal also which may go to analog outputs or may go to digital modules which create a lot of capacitive loading on the circuit. Therefore, I need drivers. So I have driver in the analog, I have driver in the digital part, and I have some analog inputs also. So these are the main important parts of this. For example, you can call it a mixed signal SOC. So the question is how I should put it. First of all, we start from analog inputs. So where do they come from? Analog inputs usually come from a sensor, which is the interface with the nature. So if they come from a sensor or they come from any natural resource in the nature, usually they have three specific characteristics. First, they are not very high in level, means that the level of signal is low. This is valid in many cases. Second, these signals, if we are talking about the CMOS technology, are applied to the high impedance input. Therefore, analog inputs are applied to high impedance inputs. See, double effect. You have a high impedance node which can pick up noise. You have a low amplitude signal which is entering into the circuit. Therefore, you have double problem. And then it goes to some conditioning circuit, some processing circuit. Usually this processing circuit is a low swing, low voltage module. Low voltage in the sense that we are talking about analog signal. Therefore, analog signal is not a rail-to-rail signal always, specifically at the input and then at the preliminary processing stages. Then you will have high swing modules and then finally you will have driver modules. Now, as you see, the way we keep them sensitive inputs, and for example, you may have buffers at the input and any sort of just input stage without any specific processing, which captures analog signals. So this part of the circuit is very sensitive. And see, it has a maximum distance with the digital output, which comes from output driver. So always you keep this as a rule of thumb when you want to floor plan your chip and your design. So keep maximum distance between these two. In fact, a digital output, which is coming from a digital driver, is the worst output with respect to switching noise and any other source of noise which is coming from the circuit operation. And analog input is the most sensitive. So this is the first rule of thumb. The second rule of thumb actually is in the way you observe these modules. You put low swing close to sensitive inputs, low swing modules. Then you go with high swing modules and then drivers. So these are here. And then if you have analog outputs, you try to keep them separate quite far from output drivers of digital part. So therefore they are still far away from each other, but they may not be too far as compared to analog inputs and digital outputs. Then whatever low speed modules you have in your digital circuit, you keep it close to analog section. Then you go with high speed modules and then finally with final drivers. Okay? Of course, sometimes happens. For example, you may have a power amplifier even in analog section. Therefore, that power amplifier also should be far from the sensitive input, right? So, if it is on the left top corner, power amplifier should be on the right bottom corner. So, this is just an example, like how you will floor plan, a simple preliminary floor plans. And the way I put my pins exactly will be like this. Means that now this digital outputs will go to the pins which are at the bottom. Analog inputs will come from pins which are at the top. And then analog outputs will go to the output pins which are on the right. So this will give at least a preliminary provision or preliminary precaution about interaction between switching noise which is coming from digital section on the analog section. So now how this interaction happens? Interaction between these two modules happens from different ways. One is from interconnect lines where you have coupling capacitances. One way is through substrate because after all these modules have common substrate. If you are able to have two separate wells, that's much better. But usually it is not possible. Therefore, if process forces us to have a common substrate for everything, this common substrate is a source of noise. Because doping in the substrate is not very high. Therefore, effective resistance of substrate is not low. This is one point. The second point is, substrate has a lot of parasitic capacitance with the entire transistors, right? Even with wells. Therefore, you have a distributed RC. And this distributed RC actually couples many modules in the circuit together. Therefore, you may feel that, okay, everything is well separated, then you have to be careful how they are connected through the bottom of the wafer, which is in fact the substrate. Therefore, that's why we have to be careful about guard rings and shielding also. Okay, before going to this, just I have a simple example. Just I did some calculations for you to get an idea of how will be this coupling important. Okay, suppose I have an analog module, okay, and this analog module have a high impedance mode. Okay. For example, this happens a lot. The input, usually you have a differential input. This can be a differential buffer, can be anything. Okay, but usually these nodes are high impedance nodes. Now, suppose you have some sort of coupling through some parasitic capacitance from a digital source. Okay, so there is a switching happening at this node, which is coupled to this node. And just to get an idea of what will happen, suppose the speed of switching here is 1 volt per picosecond. Okay, 1 volt per, not picosecond, in fact, 100 picosecond. 1 picosecond is too fast. Okay, so this is a typical value, right? 0.1 nanosecond, I have 1 volt change of the amplitude. It's a very typical switching for a high-speed digital circuit. So this means that transition of 10 to the power 10 volt per second. Okay, and suppose value of capacitance is 20 femtofarad. Okay, this is just an example. So we assume there is no coupling or effective coupling from this switching node to this input node. Okay, if we assume this, then this means that the input node should not observe as such any change, right? Therefore, effectively means its voltage is almost constant. Therefore, I can calculate the current which is injected to this node. Now I calculate this I. So I will be C dV upon dt, which will be 0.2 milliampere. So simply you inject 0.2 milliampere to the circuit. But if you are injecting 0.2 milliampere to an impedance which is high, then practically it is impossible to consider this positive input is unchanged. Therefore, it will sense a lot of noise. Just you consider it's just 1 kilo ohm resistor, even it's a very small value, right, for a high impedance one. 1 kilo ohm into 0.2 milliamp. So you have 0.2 volt switching noise, which is too high for analog signal. Input is millivolt, then it is done, right? So circuit won't work. So it's very important. I mean, these points are very important practically. That is the reason, like, usually mixed signal circuits may not work and may not satisfy all specifications in the first try. It's very difficult. Now the question is, okay, so why only capacitive coupling? We can have inductive coupling, just the dual of this effect. Why in CMOS usually people are talking about capacitive coupling? Why not inductive coupling? That is also another point. So then consider, suppose I have a parasitic inductor of 0.1 nanohenry. Again, I have considered a large value. Okay, and suppose this experiences a di upon dt of, this is again a typical value, see 100 microamp in 50 picosecond. It's a typical value, 100 microamp is quite typical for a digital circuit in 50 picosecond. Okay, this will give me 2 into 10 to the power 6 ampere per second, slowing in the current, right? This is the transition speed of the current. Now, how much will be the voltage which is generated? This will be 10 to the power minus 10 into 2, 10 to the power 6. This is just 0.2 millivolts. Therefore, in CMOS technology, actually capacitance is important, not inductor. In fact, it's very difficult to make inductors and transformers in CMOS technology. Therefore, inductive effects are much less, except one case, which is the bonding wires, which goes from pad to the pin. That is the only part of CMOS technology which makes, in fact, inductive effects very important and effective. No, this is like that. No, this is different. Because when we are talking about inductor, then we have to consider it is series with a branch. I want to see I have a branch, okay? Something is connected in this branch between these two nodes, okay? This is, for example, node 1. This is node 2. And then I have some inductive effects between node 1 and actually the input node of this module. I want to see how much will be the difference between this real node, node 3, and this node 1. That is just the difference of 0.2 microfarad. It should be in series. Okay, if you have two loops, then you are talking about this impact, right? Transformer impact effect. Yeah, no, that is different from what I'm talking about. I'm talking about this effect, okay? You have a single inductor, series with some in a branch. See, capacitance is parallel, inductor is in series. Effect is like that. Yeah, that is also possible. But actually, this mutual inductance, even if less than that, to make a mutual, that's why, otherwise, actually, everybody could make solid state transformer. That is one of the reasons it's very difficult. I would say that if you want to look at the order of impact, first is C, then is L, then is N in CMOS technology. It's very difficult. Essentially, see, look at it in this way. If it is very difficult to make L, naturally it should be more difficult to make M, right? M is a function of L. L already is low, and M is not perfect. If you know in transformers, because of the leakage of flow, magnetic flow, always mutual inductance is not perfect. Therefore, we have a lot of loss because of that leakage. So already we have a low L, and then now M also is much less than 1 upon root square L1, not 1 upon, root square L1, L2. Therefore, effectively we get even less effect of M. So that's why we should be more cautious about capacitors rather than inductors. That was only one point, just I wanted to show you like how it will be important. Okay, so now coming back to this, therefore like I will keep my modules like that. When I'm talking about high swing modules, for example, if I have a comparator. Comparator is a high swing module scenario. Or I have a rail-to-rail power amplifier or output driver. Now, where are inductors? Inductors are important when I have a pin connected to a pad through a bonding wires. This is bonding wire. Here is the where I have problem. So see, the same scenario I showed you in the previous written slide. There is an inductor series between pin and pad. This is bonding wires, okay? Then this is just considering, okay, it is a VDD. It can be a signal, high frequency signal. There will be similar impacts. Now here I'm talking about VDD and VSS. So we have this inductor connected from this VDD pin to internal pad, which is internal VDD pad. Then there is a small resistance here. Then it goes to analog circuit. So same VDD I'm using, and I'm giving it to digital circuit. First of all, I can have two different pins, but at the end I connect them together. Then that means that I have externally on the board a single VDD, which supplies my chip. I'm not going to two different VDDs because I could simply disconnect this line and connect the VDD analog here, the VDD digital here. Usually this is not recommended. The main reason is because after all, these analog and digital modules have same substrate. And then if they don't turn on simultaneously, then circuit will face problem of latch on. Therefore, it is not recommended. It is recommended to use same level as long as levels are compatible. Means I want 2 volt, therefore it's compatible. But if I need 2 volt for digital and 5 volt for analog, then there is no way, right? Of course, there is one more way. I can put a boost converter on the chip. I can use 2 volt and then boost 2 volt to 5 volt internally. That is even better. Now, anyway, so now, but here, if you notice, we use 2 different pins to separate digital and analog supply right from the pin side. The reason is because VDD line and ground line or VSS line in analog usually is not very noisy. It's quiet. It's clean. But in digital, it is fully noisy. Therefore, we want to separate them right from the beginning. Okay, so this is one of the reasons we have this connection. Therefore, we have the entire analog modules on one side, digital modules one side, and this side is again VSS connection in the same fashion. Okay, I will explain what are those capacitors. Right now you ignore. Suppose there is no C1, C2, C3. Now, I have a very high switching current which is drawn from VDD, right? So now I have a lot of DI, a high DI upon DT. So what happens is, because of this high DI upon DT, the example I mentioned was 100 microamp with 0.1 nanohenry. Now if you consider it is around say 1 Henry and the current is in the range of tens of milliamp, right? Then this voltage will increase. Therefore, you will have a lot of drop here. And this drop is not a constant drop. It just depends on the switching. Therefore, you will see this bouncing on the VDD as well as VSS line in a digital circuit. And analog circuit is almost quiet. Therefore, this is one of the problems. Okay? Of course, coming to C2, you know, if you have done board design, you know, always we connect the big capacitor from VDD to VSS on the board. This is the reason anyway we want even to, from outside, from the board level also, to short circuit VDD to VSS at high frequencies. Means that there is no noise or difference between noises which present on VSS and VDD. At least we can keep them at the same level. Means that we want to keep the DC difference constant. Now, and we want to have same AC, means that essentially their difference we want to be constant, not DC. Essentially difference to be constant. Because suppose if I have a VDD and VSS which follow each other, right? That's okay. Suppose even slowly they are changing. It's just a matter of level shift, right? After all, nothing happens. As long as external circuitry don't suffer, that is fine. But what is C1 and C3? Okay. So why do I need? C1 and C3 are on chip, C2 is off chip. So this C2 plays a role of like a low pass filter. In fact, if you include a small resistance of wires on board wires, then this will be like a low pass filter. So that is fine. But what are C1 and C3? So if I don't have C1 and C3, therefore I will have a noisy and in fact all the time switching VDD and VSS for digital circuit, which is not recommended. And even it may happen for analog if I have a lot of high power modules in analog part. So what we do? We should have two big capacitances on chip, which are called decoupling capacitances. What do these capacitances do? See, when I have a current and this is a switching current. So this switching current will flow through inductor and will create a problem. How I can divert this switching current to come from somewhere else? This is the reason we put this capacitor. How it works? If you consider a DC, okay, so DC value of this capacitor and assume this capacitance is very large. Therefore, DC value stored on this capacitance is VDD minus VSS. This is in fact the difference between max and min voltages I have in the circuit. So in fact, look at this capacitor as an internal battery. Okay. So then when this circuit draws a current, this capacitor simply can inject AC current. Therefore, the amount of AC current which is injected from inductor which is drawn from inductor will reduce. And therefore, we will have less bouncing on the line which is coming to the digital circuit. So decoupling capacitances should be enough large. Otherwise, what happens is they will get discharged quickly and they cannot maintain the voltage which is supposed to maintain across the circuit. So that is an important point. And the current which is drawn from these capacitors also should be enough large. Therefore, these capacitors should be large. So putting decoupling capacitance is quite a normal tradition in all mixed signal and or fully digital circuits. And then it's very easy to do it. In fact, you know, we have filling room. density of metal 1, 2, metal 6, metal 8, or metal 12, whatever number of metal levels we have, layers we have, should be more than some value. And to stitch to this value, then you can just use this, put a lot of dummy capacitors just between VDD and ground. Yes. Yes. Externally they are shorted, but internally they are same. No. See, consider you have an IC which has two VDD pins. Then you connect them on a track, PCB track. They are shorted. From outside they are shorted, but from inside they are not. Therefore, if there is a switching current, which is coming from this module, that will come only from here. See, because outside track doesn't have a very high impedance, right? We assume that we have designed the board in such a way that VDD line is quite a perfect line, a wide line, and straight. It doesn't have as such inductive effect. Therefore, effective inductance will be wire bond inductance. If we have an inductor here, then actually PCB design is not correct. There are many things also with the design of PCB associated. Okay, so then, in fact, these two rule of thumbs will give you an initial idea of now how you should keep your modules, and then how you should consider VDD and VSC. So this means that it's better to have a separate on-chip VDD for analog and separate on-chip VDD for digital, and then externally you connect. Okay? So now what do we mean from guard ring and what do we mean from shielding? Okay? So if you have sensitive analog modules, you keep all of them in a single well or in a specific region of substrate. The reason I'm saying the second option, because if you are, suppose you have a single well process and well, then you are not able to put NMOS transistors inside a well because they are all inside substrate. Or even if they are inside P actually makes a very robust junction with substrate. So you keep them inside one well-defined region, means close to each other, okay? Therefore, you can surround them with a bias. So what is this bias? This is called guard ring. What is this? Suppose if this is a P substrate region, okay? I put a P plus implant here, all P plus region. The same region you use for source and drain of CMOS transistor. We use it, put a lot of contacts there and connect it to analog VSS. If this is a P. If it is an N, then you connect it to analog VDD. So therefore, at least this area is well biased. What does it mean? It means that the entire substrate which is beneath of this circuit is connected to VSS or VDD. So it is almost biased properly. Therefore, if there is any switching noise which is coming from digital side, it is stopped here because it is already biased. Therefore, this is like a barrier for digital for switching noise which is coming from here. So it is like that you create a low impedance node everywhere around this area. So all these low impedance nodes which are connected at the end to analog VDD or analog VSS will dump the switching noise here. Similarly for digital modules. For digital modules also it's better to do it. The reason is they are source of noise. We don't want to protect them. We want to avoid them to transmit this noise to other places. Therefore, for digital modules, we put a guard ring just to avoid noise transmission. And it's better even to have a double guard ring. For example, if this is an N well and this is an N plus, and outside this P, you put a P plus also here. You put a P plus here. Therefore, now you will have a double guard ring. So that is much better. So always put a guard ring. Suppose if you have a very huge switching module. For example, you have a cascade of buffers, which is very common in digital design, right? Clock driver. So clock drivers should be inside the well or inside the region, well surrounded with guard rings to avoid transmission of switching noise from these buffers to other areas of the chip. But this is not enough, right? Because we'll have a lot of interconnects, many interconnects in the circuit, which can actually couple noise to each other, switching noise. Now, how to take care of those? That's why here we have to take care of shielding. So, suppose first method of shielding. Suppose I have an analog signal, okay? Analog signal, say at the low level, metal 1 or poly. Okay, this is cross section of connection. Then I have insulator. Then I will put analog ground as a shield on top of this, okay? And then digital signal will be on top of analog ground. Therefore, analog ground now is shielding this metal line from digital signal. So this is a example of shielding. So 3 metal layers, analog ground is the shield. Or for example, top view, okay? See, if you look at cross section, they are stacked, right? Metal 1, metal 2, metal 3. You may have all metal layers in one level, but still, metal has a thickness. Therefore, you will have sidewall capacitances which can be coupled to each other and fringe capacitances. Therefore, again, here we do same thing. I have a digital signal, I have an analog signal. There is no way both of them should be routed from this channel. Therefore, I put an analog ground in between. Always, of course, we use analog ground or analog VDD for shielding your analog signals. And usually this, I have shown them by the same bit, but usually this is very wide, this analog ground line. Essentially, all supply line, VSS and VDD, should be very wide compared to signal, because they should have a very small resistance. And high capacitance is better, right? We like to have a very high capacitance. In fact, if you use very wide lines, you are increasing C1 and C2, which is good. Yes, analog ground is connected, in fact, to analog pin, analog VSS. Internally, no. Internally, they are quite separate. There is no interconnection between this line and this line. Yeah. Level, no, it's not at 0. Actually, if VSS will be, analog VSS will be at 0, digital VSS will not be at 0. It will be actually a signal, something like a sawtooth. Similar to sawtooth, you will observe on the signal. Yeah, here you see they are shorted. From here, correct, but here onwards, these two are not same. In fact, here also they may be same, but from here onwards they are not same. No, see, you look, for example, here this circuit, digital circuitry, is injecting a lot of current into this inductor, right? Therefore, now, right from here, you will see a difference between analog VSS and digital VSS. They are not same. And even if the analog also injects noise, these two are not same. The amount of noise which is injected here and here are different. And of course, this coupling capacitances will reduce because now they are also injecting the AC current, which will reduce this AC current. Here. Then you will have one common inductor, right? No, still you need a bonding wire, right? To take it out, you need a bonding wire. But the problem is with inductor. We need to separate them, right? Because of inductor. So we need to have to separate inductors. To separate inductors means two different things. C2 is external. That capacitance we keep always on the board between VDD. No, this is on the board. No, shielding. See, what we do in shielding, suppose you have a signal line, okay? This is a signal, and this is also another signal, okay? This couples because of coupling capacitance, some noise on this line. So I want to shield this in such a way this gets protected, right? So what I do in conventional case, for example, in BNC or coax, we put a cover, in fact, which will be ground VSS. Is this connected? So it is shielded. Here I cannot make a cylinder. So what I do is I have this signal line. I put a ground here. So it is like that. I just have kept, instead of around the wire, I have kept it on top of the wire. Still is this okay? Or I keep it on the same level adjacent to the wire. So this is shielding. But here, this capacitance creates, at high frequency, what it does is, it makes a short circuit, right? And it's able to draw all switching currents without showing any as such impedance. What does it mean? It means that if you have, suppose this capacitance is too large, very large. What does it mean? It means that in DC, it's open, in AC, it is short circuit, right? Therefore, means that in AC, VDD and VSS are same. When we say they are same, what does it mean? It means that these two will follow each other. And that is enough for us, right? We want to have two rails, which are, of which the DC difference is a constant value. Or even if, DC difference is a constant value. And here DC difference is a constant value. Because if VDD increases, VSS also will increase by the same value. Because there is a short circuit. And there is a, for example, if you put a sine wave on VDD, okay? You will see same sine wave here without any phase shift, ideally, if C2 is too large. So this means that VDD and VSS are working together. So circuit, as long as, in fact, circuit won't observe this variation, because from circuit point of view, we are talking about relative potential, right? We don't have any absolute potential. VSS is just a reference. As long as my VDD is constant with respect to VSS, that's enough. So it is, that's why it is called decoupling. In fact, it decouples noise which is injected from any modules on VDD and VSS. Decouples it. So this is not for shielding. Maybe because it is drawn like this, then you thought it's shielding. It is off-chip capacitor. It's not on-chip. Yeah, one more thing that usually in the layout, we have to be careful in analog layout, specifically is if we have two transistors which need to be completely matched, we have to make the layout in such a way these two transistors will observe same variation. Okay. Now, of course, if you look at Razavi book, you may have seen there are rules like how to generate different interdigitate layouts or command central layouts. So these are very simple. That's why I didn't mention it as here. For more study, you can look at layout portion of Razavi book. But one thing which is very interesting, and you want to have an idea really how much will be the offset, right? One way, of course, will be to simulate using variability data which is given by the foundry. But there are ways actually to calculate this value. First of all, it can be shown that any variation on any parameter, okay, in a CMOS transistor is proportional to root square. This should be root square. This is square root, sorry. This is square root, okay? You just correct it. This is the square root of area of gate. And these parameters, like essentially this AY is a process parameter. And delta Y effectively is actually standard deviation. So, for example, for Tiox 10 nanometer, as per Razavi data, this parameter is around 10 millivolt into micrometer, right? Unit of this should be volt into meter. So therefore, if you know this parameter, then it is very easy for you to calculate really what should be the mismatch. For example, if I am in this technology, which is almost 0.6 micron technology, I use L 1 micron and W 16 micron. So I have two transistors with these sizes. But what will be threshold voltage mismatch? It is around 2.5 milliwatt. This is a very good rule and formula to calculate matching. It means that even if everything is perfect, this is of course random mismatch. Random mismatch due to, for example, threshold voltage only will be 2.5 effectively milliwatt. Interestingly, this value reduces as oxide thickness scales. In fact, this value is proportional to T oxide. But at the same time, when we scale technology, we actually use smaller L and W unless we don't have any problem with input capacitance. Therefore, we can add speed of the circuit, which is driving this circuit, and parasitic capacitances inside this circuit. Therefore, we can increase W and L as much as we want. So, just as an example, okay, so how really this helps, okay? First of all, when you increase area, you actually doing more averaging. What does it mean? Means that you have more number of samples. Simple, right? You consider you have a transistor and its area is W into L. You divide this transistor to an array of or parallel combination of or series combination of smaller transistors. Each one of them is like a sample in this statistical domain. Now you are increasing the number of samples. Therefore, you are increasing, you are doing more averaging, or you are doing averaging over more number of samples. Therefore, it is likely to have a better value of matching. What does it mean? It means that effectively, when you are increasing the area, both of them have same number of samples with the same distribution of samples. Therefore, their average should be similar. So, this can be easily, for example, proved by an example. So, for example, suppose I have a transistor L and W. Okay. So, what I do, suppose I keep one of them constant and I change the second one, because W, if you keep W, L constant, W different, and change W, then it's very easy to prove it. I go with a more difficult case. Suppose W is constant and I increase L, okay? How this mismatch will improve, okay? So, first of all, when I say mismatch, means that none of these transistors is actually a transistor with a length of L, right? One can be L1, one can be L2. I have two transistors. So, I focus on one transistor and then I will see how the increasing L will increase number of samples. Therefore, average value actually will, standard deviation of, in fact, variation will approach to 0. Therefore, L will be L or nothing else. Okay, so then you consider you have a set of transistors and then with a, so I just consider I have a set of transistors and say n number of transistors. So the total current will be okay, so I just consider I have a set of parallel transistors with different values of L, but these L values are similar. So the point is that suppose W constant means that no variation, okay, but L observes some variation. When L observes some variation, what does it mean? Means if you look at layout of transistor, this is L, This is W, right? So I have change in L. What does it mean? For example, the first thing will be poly roughness, right? Because of this roughness, actually I don't get exact L, right? Everywhere, if you choose a sample, what do we mean from sample? If you divide this to n number of strips, okay? Therefore, one will have length of L1, one will have length of L2, and so on. And each one of them will have a fixed W of say W upon N. So fixed W. W doesn't change. Okay? So L is changing. Okay? So W is constant, but L is changing. Therefore, effectively, I consider I have a constant W, but because of this roughness, for example, somewhere L is like this, somewhere L will be like this. Therefore, here is L1, here is L2, right? So, therefore, I have n number of parallel transistors. Okay, so this is that n, and then I just consider I total will be summation of these values. So, therefore, therefore this I total, I consider W doesn't observe any change and any variation. Therefore, it will be mu C ox W, some W star I put because this W is actually delta W. It's not W. W upon N is W star, but it's constant. Okay. So suppose this is the current mu C ox W star, and some bias also I have VGS minus VT, or it is in saturation region, whatever. So what is important is I total is proportional to this ratio, right? So according to the bias for these transistors. So so if I want to write real current, in fact we should write this I is proportional to this. Therefore I total, which is summation of Ij, can get converted to some constant value. I use the constant B. Okay, includes all these coefficients. So P, some constant W star upon Lj. So therefore, I just divided this transistor into n parallel transistors with a fixed W and L that is different because each strip will observe some random variation of L. Okay. So therefore, I will have this value. Now, therefore, I consider each Lj is some L plus some delta L, right? Which is related to that Lj. Okay. So L is the value that is drawn in the mask, on the mask. So therefore, just I will replace, it will be, B is a constant, okay? And W doesn't observe any variation. So this will be L plus delta L. Okay, I take a factor, therefore I total will be B W star upon L into summation J as if 1 to N, 1 upon 1 plus delta Lj upon L. And of course, you know, if I have a number x which is very small, I can approximate this 1 upon 1 plus x to 1 minus x. If absolute value of x is very small. Therefore, I can write it And I want to see what is my equivalent L afterwards, right? Which will give me the same current. So I will make these two equal, therefore L equivalent. By the way, I should put the number n here. W star was the width of one strip. Therefore, I have n parallel strips. Therefore, it should be n into W star. So it will be n into W star. So L equivalent will be equal to L upon this summation. J as 1 to n, 1 minus delta Lj upon L. L equivalent is to will get into n. Okay, of course, summation of J as from 1 to n1 is equal to n, right? This n? No, for L equivalent, effective W will be W star into n. W star is the width of one strip. See, this is the strip, right? You have n number of strips with the width of W star. No, I'm not increasing W. W is constant. Just I have divided the transistor into n number of strips in parallel. And all of them have width of W star. W star into n is equal to W. And now I want to see what is the equivalent L I get if I have variation in L. Right? No, L equivalent is the equivalent L I can put here without any variation. And with the width of W, which is equal to W star into n. No, this because these are for width of W star. But this is for the width of n into W star. W doesn't have any variation. I have divided it into n number of strips and each one of them has the width of W star. W star is W upon n. W star is W upon n. Now, after all, I have a single transistor with the width of W, which is W star into n, upon L equivalent. The remaining part remains constant. Got it? No? Okay. So explain. Come explain. W is a constant. It doesn't have... Fine. Okay. Now, this side is total current of n parallel transistors. Yeah. And W is W star. Okay? Great. W is W star. W is W star, not W. For this left side. Summation is here. Right? Now this is n into W star. For the right side, which is a single transistor. See, you have n number of transistors. This is W star. This is L1. This is L2. With a little difference from L1. And again, this is W star. They are all parallel. So therefore, the current will be summation of this current. This side is fine. Do you agree if I want to make the entire this parallel combinations as a single transistor, width of that transistor will be W star upon into N, which is in fact W, right? Correct? Convince? Okay. So therefore L equivalent will be this. Then we will just, okay, I will write it like this. This will be summation of j from 1 to n1, which will be n, minus summation of j from 1 to n, delta Lj upon L. Now I remove n, therefore it will 1 minus 1 upon n summation. See, you see here interestingly, I am getting average of delta Lg upon L over n samples, right? This is exactly what we are doing. And then just, now I return it back to the original case. I use again same thing, therefore it will be L into 1 plus summation j from 1 to n delta Lg upon L. So now my L equivalent is original L plus this there, 1 upon n also. Average of relative value of this change of L, which is delta Lg upon L. This is relative change, right? And L is actually the average value of all this. Okay? So L is actually average value of this total L. So therefore I have this, right? So therefore this is actually L equivalent. So then now what will be the standard deviation? Because what makes offset? Offset actually is the standard deviation, right? Twice of standard deviation, third time of the standard deviation. It depends how much window we want to consider. Therefore, I will just calculate the average of this, right? So L equivalent. What is the standard deviation for me? Because see, then now this shows L equivalent is a random number, right? If I increase number of samples more and more and more, this summation actually will approach to 0. That is what we want to prove. Means that if you have two transistors and then you choose a long L for both of them for a given W which doesn't have any variation, you will get better matching. Well, in other words, each one of them will have a L equivalent to L. Therefore, two L's are same. Means that none of them will observe variation because L is too large. We are sampling with a large number of samples. N. So just we calculate this standard deviation. This means average. This bar. Don't confuse it with fraction. Okay, so then this will be L equivalent. So L average of course is L square. Just I replace, I don't write the replace what should be, but then finally you can derive it, okay? I suggest derive it. I have written here. If you want, I will write. See, there is nothing actually specific to just replace L equivalent with this L. See, what was L equivalent? Was L plus this there, right? Now I replace it, this two L will get cancelled, the remaining part will remain, this there. Therefore, I will get this average, 1 upon n square into summation j from 1 to n delta Lj square. And this is effectively 1 upon n sigma L square upon, just that's it, sigma L square. See, what is this is how it comes here. It's 1 upon n square into this average of this there. 1 upon n square is constant, average of this there. square. Sorry, this should be, sorry. Wait. L equivalent is equal to, I think I should write it. The best way is to write. I write it in detail. So, L equivalent is L plus L upon N is summation. Okay. Now we will replace it in this relation. So I use average also so that, so L equivalent minus L average, right, square. So it is L minus L minus L upon N is summation. Square. So these two will get cancelled. And this term is constant. I will take it out. So it will be, and this is just L square, right? And this is also L square. These two will get cancelled. It will be 1 upon L square average of this J from 1 to N delta Lj square. Okay, and then now if you look at this is definition of standard deviation, right? Standard deviation of L is average of is this, right? When we have n samples. So it will be sigma Lj, sigma L square upon now these two get cancelled. Now you have one term. Okay. Yeah. It will be, yes, sorry. So it will be this, right? Yeah. Correct. So in fact, that is the case. Right. Correct. So what does it mean? Means that if I have a standard deviation for L, if I increase L, in other words, I'm increasing N, right? Then I actually get less standard deviation for equivalent L. That means that total variation in the transistor will reduce if I increase that area. And actually, this is one thing that, Pilgrim. Pilgrim actually has interesting papers from 1989 onwards. He has actually developed this theory. Like if I increase area, then how this mismatch will improve. That's a very interesting theory. I was just curious to see how this can happen. That's why, and I saw in Razavi's book, it's given for L, because W is easy, right? The L is on the denominator, so it makes it more difficult. But just I was curious to see how really it happens. So that's why I try to derive relations and share it with you if you are interested to see how this is getting derived. So you look at Pilgrim papers. And then this coefficient also, this parameter. For any sort of parameter you have in the transistor, for example, threshold voltage, mobility, Cox, or even sometimes they combine them together and then they report it, are given in many papers. If you look at Pilgrim papers and papers who have given reference to Pilgrim papers, you can look at citations. You will get all this data for different processes as long as they have been reported in papers. Sometimes foundries don't report it. Okay, this was just as an interesting example to see how area will improve matching. Okay, so now we want to start PLL. So any question if you have for this part? If you have, you can ask, don't worry. Yes. No problem. Of course, what you say is correct, but the point is, it depends first of all, what is that line? That is correct. For example, if you increase this capacitance, and suppose this is an output line, okay? Usually I'm not so interested, of course, to make output line, it has a lot of swing, but suppose if it is, and it's already driving a big capacitor, right? Therefore, this capacitor is not so important. But it happens that it may be a low swing signal, which is coming from an intermediate stage. It's going to the next stage. Then yes, I have to be worried about this. Is that? To shield? See, shield itself means, in fact, I use another wire to shield the second one. But then now, if you want to say that how I can do it, see, in any manner you do, anyway, you are introducing a new capacitance. Either you do it in one level, or you do it vertically or horizontally. You are increasing the capacitance. You mean that I have a node, okay, which is very sensitive to capacitive load, right? I don't want to impose any capacitive load on the node. Of course, in analog, we don't have such a system level like what we have in digital. But it may happen. For example, if I want to use one single bias, which is not even recommended, of course, nowadays. But anyway, and then I want to rotate an analog current for a long distance. And then I don't want, but if I want to rotate for a long distance, then this means that that node should be able to drive a long capacity, you know. These two cannot happen at the same time. If you want to rotate for a long distance, means that whatever module is connected to that line is able to drive this interconnect. Therefore, this means that it's okay for me to put those capacitors also. Therefore, this means that if it is not possible, I have to add a small driver to that module. There is no way. Yeah, exactly the same thing I told him. Yes, but look, if you are really transferring a signal, analog signal from one corner to another corner for any reason, which usually we don't prefer, but if it is the case, then means that already we are having this in mind that I have to drive this interconnect. Now, if I have to drive this interconnect, I make a small driver at the output of that module. And then I assume that whatever additional parasitic capacitance I will have here, I will add to that driver. There is no other way. This is actually what we do. Local drivers always use for all local interconnects. And of course, global interconnects will have, but local interconnects, as long as the signal is of importance, they will have their own local drivers. Yeah, this will add RC value. But already RC is here, right? Anyway, you have this RC. And even if it is, suppose this is an analog signal here, it is metal 1. You have an insulator here, and then there is a substrate which is connected to ground. Already you have this capacitance, right? Which? No, this is sigma L, this is sigma L equivalent. See, okay, let us just define it like this. I am just what I am doing. Okay, yeah. Look, put it in this way. I have one transistor with a width of what I call it W star. Okay, one just simple string. Okay, this has my minimum area. Okay, single transistor, and its width is W star, length is L. Okay, I put two of them in parallel. Okay, so forget about this. So do you agree this will be the standard deviation of with n equal to 2? No, this is y in cube. See, I want to get this average, right? So average of this, okay. What you say is that, yes, sorry. This should be here, right? Upon n, it's average. See, I'm getting this average. Okay, so this average itself should have this. Still, this is average. No, that is average. I mean, what is your question? See, till here we are talking about average, right? Average of this sigma. In fact, this average should be here. Average of this square. Okay, then average of this square. Okay, now what you say is that because this average itself is n upon n, therefore I can write this. Okay. Yeah. Last, actually, just was. See, average. What is sigma L? Sigma L is this, right? Sigma L is. Yes. Okay, got it. So it is 1 upon n. Okay, sorry. Yeah, correct. So sigma L is equal to 1 upon n summation L minus L star square. L bar, which is average, in fact, L average. Which is equal to 1 upon 10 summation j from 1 to n delta L square, right? This is correct. Okay, sigma L square, right? Fine. Okay, now here I have average of this, which is 1 upon, see this average alone. Average of this, which is average of this is 1 upon n square. So average of this alone will be sigma L square of n sigma L square. No, this average. This is the average. In fact, this is. This is average over samples. Yeah, this is same as here. Okay. Okay, so then just this is 1 upon sigma. Okay, so this will be average sigma L. So this is average. So this is n. See, average of this summation alone square. This will be sigma, right? Therefore, it will be upon n square. This is what you say. Yeah, but anyway, after all, this will be sigma L square, right? Right? No, see. This will be sigma L square. Right? Which here? No, but this is not summation. This is average of summation. So see, here the whole point is, if I increase the number of transistors which are parallel, I will get a less standard deviation. If you have a transistor with a width of W star, okay, and L equal to L. Now, if I make n parallel number of this transistor, the effective L of this parallel transistor will be less than a standard deviation of effective L will be less than a standard deviation of L of a single strip. That is the whole point. See, L average is the average across all n strips. You have n parallel transistors with different L's. Average of all these L's. We call it L. Yeah, L equivalent is this. See, essentially, see, that I will figure out. That is okay. Don't be, so concerned about this part. I will check it next time. I will tell you. No, listen. You just forget this part. Just look at this. If you increase the number of n, right? Effectively, your L equivalent approaches L. This itself shows that your standard deviation is getting reduced. As you are increasing the number of strips, means you are increasing your W, right? You are increasing your W. When you are increasing N, means you are increasing W and your L is constant. Constant means L has some variations. You are keep using same L. You are repeating so that you are increasing the number of samples. So effectively you will get less variation in L equivalent compared to L. That is the whole point. Means that if you had a single strip, it would have had a variation of delta L1. If you have two strips, it would be delta L1 plus delta L2 upon 2. Now you are increasing this number. Therefore, this will be this whole summation upon n. And effectively, this whole summation upon n will approach to 0. That is the whole point. I will do one thing. I will reproduce this next time. I will show you. Okay, but anyway, so at least this point is clear, right? So what is the whole point? The whole point is you have a transistor. Its width is W star and length is L, right? Now what I do is I increase area of this transistor. How I increase? I have assumed only L has variation. How I increase W number of? How I increase area? I add one more strip with the same W. Notice I have assumed W doesn't have any variation and L only observes variation. Therefore, this is L1. Now this is L2. I will continue. The whole point is, if I increase the number of strips, I am just increasing area of my transistor by increasing W. I will get less standard deviation in the equivalent L. So each one of them is L plus some delta L. See, intuitively also it is clear because you have more number of samples in your sampling domain. Therefore, it is clear your average will approach to 0 and you will get same L. Okay, let us now start. what I will do, I will write it, I will put it on Moodle. Okay, let's have some introduction to PLL. You may have seen this sentence in Rabe's book. He says a set of periodic signals of the same frequency is well defined if one of them is known, which is called a reference signal, and then relative phase of other signal with respect to the reference signal are known. Of course, just I'm adding, considering all of them have same waveforms, otherwise these two information are not considered. Maybe because he's talking about digital domain, then automatically this condition is valid. So what he says is, after all, in many systems, I have many periodic signals. For example, synchronous digital is a very good example. Now, if I have a periodic clock, and then I distribute this clock everywhere in a very, in a chip with a very large area, a system on chip, then, of course, I will have a lot of problems, you know, clock skewing and all these issues. So, his point is, if I have a reference signal, whatever it is, and then I can adjust phase of my other signals with respect to this signal, therefore I have actually my signals. It is enough for me to know what is the relative phase, therefore signal is known. What does it mean? It means that everywhere and in the corner of, any corner of the chip, if I am able, if I have a data which is synchronized with some clock, but because of delay in the interconnect, this synchronization has skewed. If I am able to generate a clock which has a very well recognized and well defined or well known phase shift with respect to this data, then I am done, right? Because I can now use that clock to process further. Because that clock actually is extracted from same data based on a well-known phase difference with the data. So that is enough. This is actually what he says. So that's a very interesting thing, and that is actually the main property of phase lock loop. What we want to know is we want to lock the phase in such a way that we are able to have that known phase difference, and therefore we would be able to reconstruct the signal. What he means ultimately, inherently, if you are able to generate a well-known phase, you have already reconstructed the signal. Therefore, if you make it in such a way, somewhere, in some part of the system, in something which is called phase lock loop, if you are able to develop that phase difference, then means that your signal is already constructed. And then you can use it. And then Resiliency defines what do we mean is, if I have an oscillator or whatever, he calls it oscillator actually, because it is talking about phase locking inside the loop, in phase lock loop. But if I can align phase of a signal with a reference phase, that is called phase locking, which is same thing that actually Rabe says, only the difference is, Resiliency, of course, practically it happens. This means you need a feedback loop after all, right, to generate this. And if the loop gain of this feedback loop is very high, that phase error actually approaches to zero. Therefore, actually when locking happens and then delta phase or difference between two phases is developed, that difference itself is close to zero. So that is another interesting point, means that not only I am able to develop a constant phase, but actually that phase is almost zero. So therefore, if I want to see how much phase shift I have with respect to a particular reference that I know it's constant, I need to have some component which is able to compare two phases. To compare two phases, what does it mean? It means that I need a differential amplifier in phase 2. Just right. So now how I can have a comparator which compares two phases, or a differential amplifier of which the inputs are two phases. So this is the basics of phase lock loop. So it is a loop which locks on a particular phase, and essentially because phase and frequency are not independent, you cannot change phase without changing frequency, right? Because frequency is the derivative of phase and vice versa. Therefore, effectively you are able to do frequency locking also. Means that your frequency also will be set on the reference frequency. And that is a very interesting result. Not only you are able to reconstruct the signal, but also you are able to reconstruct it with some well-defined frequency. Okay. So one of the very preliminary phase detectors in digital domain is simply an XOR circuit. In analog domain also we can have a simple, in fact, differential phase amplifier. We can call it. Suppose if you have a multiplier, okay, and then you apply two frequencies, omega 1 and omega 2 to amplifier. At the output of amplifier, you will see omega 1 minus omega 2 and omega 1 plus omega 2. So when you see omega 1 minus omega 2, means that you are observing omega 1t minus omega 2t, or V1 minus V2. So in fact, the multiplier is a simple example of a phase detector or phase comparator, and actually it's a linear, means that it is like really a differential phase amplifier, provided the second frequency gets filtered by some filter. So that frequency. Therefore, in analog domain, a simple multiplier can do this job. In digital domain, XOR can do, but it has some disadvantages that we will see what are the problems. But then just, if you consider you have two signals with some particular delta phi difference, then at the output you will see a pulse of which the width is modulated by this phase difference. Okay, so but then we will see that to be able, see, what happens is these two have same frequency, but they have some phase shift. Now, if you put it in a loop, which has a high loop gain, so this delta phi will go to 0. How it will go to 0? Then frequency need to change. In a feedback loop, if this is an open loop, this in open loop, yes, if you give this will continue forever. But now you make it feedback. Now what happens is you use this signal to change the frequency. Or if you use this signal, you apply it to some oscillator, which is controlled by this voltage. It cannot be a stable, you know, when a feedback loop is in a stable mode, you have an error. That error is signal divided by loop gain, right? Now loop gain is very high, so that error is very small. So therefore this delta, if this delta phi is not very small, therefore it won't remain stable in this case. So what happens is now this H should change. To change this H means frequency should change. What happens actually, frequency changes and then it comes back to this frequency. That is another interesting point. In the transient duration, frequency changes, but after all, when phase is established, then frequency settles on the original frequency, which was the reference frequency. That is also a good point. If you have two frequencies, they are already same. But there is a phase shift which is large. Frequency will change, phase shift will get corrected, again frequency will come back to the original frequency. So we will stop it, we will continue next.